Hello, and good afternoon. Presumably you can hear me okay with this. So I apologize for being the English speaker with the weird Irish accent, but I came to Paris. It's a lovely city, and thanks for having me. So this afternoon, I want to finish off, and what's been a really good conference so far, and people who come to conferences tend to think a little bit differently than some of the people I'm going to talk about in this slide. I spend a lot of my life dealing with systems, trying to make them go very fast. I have the pleasure of working on some of the fastest systems in the world, some trading systems where we're down to tens of microseconds in response time, dealing with millions of events a second. And I keep finding loads of folklore in this industry, and this is what I'm going to talk a little bit about. In particular, I keep seeing what I kind of term as the fanboys. We see this quite often. People who just believe in stuff, and they believe in it because they just don't follow science. This is one of my heroes, Richard Feynman. Very, very interesting guy. Done all sorts of interesting things, like won Nobel Prizes for physics, sort of learned to play drums. He's done some really, really interesting things in his life, down to even having relationships. Like most of us techies and nerds, we'll struggle having relationships with the opposite sex. Richard Feynman had these issues as well, but he decided, how can I experiment to get better at this? And so he experimented lots over and over again to work out what works and how he could have good relationships. And then he had a number of good relationships. In fact, some of his wives probably said he had too many relationships, and how he actually acted. And what he discovered through experimentation is, if you make women feel good about themselves and you make them laugh, that's all that really matters. It says it took him a whole lifetime to work it out, but it was fun doing it. Now, Richard Feynman wrote a couple of interesting books, and in one of them he talked about how in our modern world he would love to show Galileo this world. But the thing that sort of started to occur to him was that our world is so not scientific. We don't test, we don't measure, we don't do lots of things we should. So kind of as a disclaimer up front, some of the stuff I'm going to show you today, I might be wrong on. Measure for yourself and sort of follow good science, and you'll get the answers. So this is what he would like to have said to Galileo. What's much more interesting is something his dad said to him. At one stage, Richard Feynman was asked, what is the most important lesson you've ever had in life? He made jokes about, well, how to sort of do much better with women, but he says, whenever he thought about it, the really serious thing was his dad taught him the most important lesson. His dad was not a scientist, his dad was a salesman. And when little kids are so curious, and they're always asking, why? How does something work? How does it work? His dad would never give him the answer. What his dad said was, how would you design an experiment to answer that question for yourself? And by taking that approach, he found that he could work stuff out. This is a kid who, by the time he reached high school, had worked out trigonometry and calculus for himself. Not because he wanted to learn math. He wanted to do other things that were fun, and the math was needed for it. So before he was even taught, he had worked this stuff out for himself. He's a bit unusual, a genuine genius in the world, but it's interesting what he learned. Now, what I'm going to talk today about is folklore. And folklore is just where people believe stuff that's just not true, and it becomes so common. Our industry is riddled with folklore. And so I'm going to have a little bit of fun and talk about my top 10. It's a good excuse for me to rant and have a bit of fun at the end of the conference here. The sort of things that I see so often and hear people say, yet I find are just not true quite often. So let's jump into it with number 10. We'll all have heard this so many times. CPUs are not getting faster. Herb Sutter wrote a great paper on it called The Free Lunch is Over. It's really interesting. After Herb wrote that paper, I was finding this isn't exactly true from what I'm seeing. And so I'm one who believes in measuring stuff. So one of the things I've been doing ever since Herb Sutter wrote that paper is writing some little programs and testing CPUs. I do this all the time. I test CPUs, test networks, test disks, test lots of things just to see how they work. So let's take the book of Alice in Wonderland and go through and split it up into words and put those words into a big array. It's a kind of interesting little CPU-intensive test that you can actually do. Well, if I run this on the last 3 generations of Intel processors, this is how long it takes. Notice? So the premise CPUs are not getting faster. Does this hold true? Now, what these operations are is how many times per second you can tokenize the entire book. Not how many tokens per second. This is tokenization of the entire book. I can do it. Like starting from 1,400 times a second up to 2,674 times a second. Going forward with CPUs, those are 3 generations of Intel microarchitecture. Okay, now they're not getting faster on clock speed, that is correct, but they're getting faster on actually processing data. So people are saying this, and people keep repeating this, but if you actually measure it, is it true? This is not showing it. Let's dig in a little bit deeper. If I run a program, I can actually get the CPU to give me a lot of counters on what it's actually done and the time it's taken to do things. This is the output of a program called perstat. You can give a lot of options to this to get it to tell you lots more about what's going on. But I want to pick up on a couple of things. So this is whilst running the tokenization of Alice in Wonderland, how long did it take and how many different counters went up on that CPU. So there's a lot of text and stuff on here, but I want to pull out a couple of interesting things. First up is how long that test took to run. And this was on the Intel Nehalem microarchitecture. That is the one generation before where we're currently at. I'm going to show you the current generation after this. It's taken 5.9 seconds, nearly 6 seconds to tokenize that book a number of times. It's actually quite a few thousand times. Now, if I drill into something else, those figures are, the first one is how long the CPU has been sitting idle waiting to process instructions. And that's for the front and the back end of the pipeline. So we're saying CPUs need to get faster. This CPU isn't running flat out. As it goes to tokenize this book, it is spending a lot of its time idle. So making it faster, would that actually even make the tokenization of the book any faster? It's kind of interesting. We're going to go into this a little bit more in a second. Also, this figure here, this is the number of instructions per cycle that are being processed. It's actually managing to process 1.5 instructions per cycle. Our CPUs are actually parallel inside. This is not running multiple threads. This is only single-threaded. But it can actually parallelize even within a single thread. Now, let's go forward a generation. So on our previous generation, we were running at 2.8 gigahertz Nehalem. Now I'm going forward to a 2.4 gigahertz Sandy Bridge. So it's actually a slower CPU and clock speed. Look what's happened first. I've dropped from 6 seconds to 5 seconds to run the test. It is actually demonstrably faster. So kind of interesting, our CPUs aren't getting any faster. That's pretty significant. Something else that's interesting in this is that CPU is not idle as much of the time. It's spending less time idle, so it's actually able to do more work. And this is actually why it's managing to do more work, because the big difference between these two CPUs is not that the CPUs need to get any faster. You can feed data to them much faster because the bandwidth from the memory subsystem is greater, so you can give it more to do. Actually, most of the time, our issues with our programs is things don't have enough to do. You need to feed them and feed them fast. Now, it's actually managing to get up to nearly 2 instructions per cycle, and that's just stepping forward a generation. Kind of leads on to the second thing I see quite often is people believe memory is random access. It's actually not an unreasonable thing. It's called random access memory. The funny thing is it really? I would recommend people go off and read books like this. It's kind of dull and boring, and it's not something the fanboys will actually go and read because it's a little bit of work. But you'll actually learn an awful lot about how our CPUs work. I didn't give a talk here on Wednesday, and I covered a lot of the issues that are sort of covered in the likes of a book like this. But fundamentally, what our processors do and our memory subsystems do is they make bets. They make bets on what our programs are going to do and try to make the code run better based upon those bets. The first bet they make is based on temporality, on time. So what they think is any data you've used recently, you will use it again in a soon period of time. So stuff that's used together in time gets used again together in time. So it keeps things least recently used being a good example of this. They also take a bet on spatial. So things that are close together tend to get used together. This again is perfectly reasonable. Fields within our classes, all those different structures that are held together, we tend to use multiple fields at the same time, so it's useful for them to do that. They also make a third bet that our code follows patterns of access. We'll tend to walk through an array. We'll tend to walk in known steps through code. And as long as we're following one of these sorts of three things, there's hardware in there that will actually start pulling our memory into the CPU before we actually need it. And so it's there, ready to go, and it's preparing for us based upon these three bets. So let's go back to measurement again. I like to take it always back to measurement. So I'm going to use this software to measure one of the latest Intel CPUs for what is the cost of accessing memory. Well, we'll make three measurements. One is I'm going to walk through memory completely sequentially in a nice predictable fashion. Another thing what I'll do is I'll jump around randomly but within a page of memory. Our systems run on virtual memory. We actually use virtual addresses rather than physical addresses, and that's organized into pages. Typically 4K pages, for example, in an operating system. So I'm going to go random within a 4K page and then move on and go random within another 4K page. So that's the in-page random. And the last one is completely random, anywhere across the entire heap. Look at our figures. Okay, within our L1 and L2 caches, it's all very similar, because that is just direct access to get to that. L3 doesn't have some of the really smart circuitry that L1 and L2 does to help us out. So as we get more random, it takes a greater number of clock cycles. As we get out to main memory, look, there's an order of magnitude between walking sequentially and going random in main memory. If I combine the behaviors of here with the behaviors of this, whenever I'm walking through memory completely sequentially, there is no latency effectively. The hardware hides it from us completely. So you can weirdly think of main memory like tape. It is not random access. So the patterns of access really matter, and that will dictate for our data structure. So what data structures you actually use makes a big difference in your program. Quite often arrays are much better than linked lists for exactly these sorts of reasons. And keeping data together that should be used together is really important, and that will be talked about later. So going on, we also hear disk is random access. That's one of the things that's always been told to us. Disk is random, tape is serial. Well, this is how disks actually record data. They record it in tracks into sectors on those tracks. As you go further out in the disk, it actually has more sectors than there are inside because it's got more space. So it actually records more data in the outer layers of the disk than the inner layers of the disk. So as it's spinning at the same rate, you actually get more sectors going under the head for the same amount of time. What's that look like in data transfer? So this is a typical 10K disk. I can be transferring up to 220 megabytes a second from the outer tracks. By the time I get to the inner tracks, I'm down to 120 megabytes a second. That is 100 megasecond difference. So just even going sequentially, there's quite a difference in its performance. Now let's go and look at it randomly. So if I go to access a disk randomly, an I/O command is made up of 4 components. There's the actual command itself that has to be processed in circuitry. There's the time to seek for the ARM. So there's an ARM inside and it has to seek to the right track on the disk. Then the disk has to rotate around under that ARM, and then you've got to transfer the data off it. So those are the 4 major components to how we get data off a disk. Now let's say I want to just access a random 4K block on that disk. The circuitry time is kind of negligible. It's very, very small. As I move the ARM, depending on your type of disk, if you're on quite a slow laptop disk, it'll be anywhere between 0 and about 15 milliseconds to seek across that disk. A fast server disk only has to seek in around 6 milliseconds because it's much, much faster. Then how quickly the disk spins. Say the disk is spinning at 10,000 RPM. That sounds really very fast, but when you get down to milliseconds, it is taking 6 milliseconds to do a full rotation. So if I want to look at, well, what is the total cost now to find my 4K block, and the transfer time is negligible in this again, around 6 milliseconds to go find a block on disk. That's how much it's going to take me in cost. So start doing some basic calculations on that. That's only 166 blocks per second I can go and fetch off that disk. That means about 664K a second versus 200 meg a second. Are disks really random access? I'll say again, probably sequential, but people believe they're random. Oh, this is one of my favorites. Who develops on a Mac? Haha. It can just be as bad. Who develops on a corporate Windows-based box? With spyware, corporate malware, virus checkers, all sorts of stuff. If we're trying to work in a high-performance environment, we're typically going to be deploying to either a Windows server or a Linux server. That's what we're going to be doing. If you want to write code that performs well, it's good to have an idea of the target platform. Now imagine you're given the job of working out, how do I drive across Paris in a truck and plot a route? Now, if you went and tried that in a truck, you would learn a lot about which roads are hard to turn around, which roads are one way, which roads are really difficult to cross. But how many people would go and do it on a bicycle to find out what the route should be? You develop on a Mac, it's actually very similar in your thinking. The scheduler works completely different, the file systems are completely different, networks completely different. In a performance world, you're not actually working on anything remotely like what the target environment is. So we also look at the hardware. Within these machines, your Mac probably has a single CPU socket. In virtually every server you'll be using, there will be at least 2 CPU sockets, and those CPU sockets have got interconnects, so our memory now is non-uniform in its access. So memory is connected to each socket separately in these machines, and so if I've got a core up here wants to access memory down here, it's typically going across an interconnect down to that, so it's non-uniform and behaves very differently and very weirdly compared to what you'll get inside your laptop or your little desktop. This is a much better way of working, is go and buy a server that is actually very similar to what you're running in live. You can buy these for a few €1,000 and you can fit it onto your desk at work. Even better, set it up with dual monitors, dual keyboards, and work on it in pairs. Now, the nice thing about these environments as well is that when you've got multiple sockets that can run really fast and lots of memory, we can also run all of our tests in parallel. We can run the whole system very realistically. So it runs fast, it gives you the same feel as it is in live. So, interesting question, should you be using your Macs? This is another great one. Garbage collection. It takes away all my worries about memory access. I started off with assembler, done a lot of C, C++, done Java since the beginning, and C# and a few other languages. And then Java does. It makes certain things much, much easier because you don't need to worry about garbage collection until you start working on systems that are reasonably big and significant. Has anybody ever tried a command like this? The Java, you can tell it to unlock all the diagnostic options and get it to print all of the flags, which are all of the options that go into the JVM. I'm just going to run this and pipe it to word count and list how many lines. I get 770 options on my Windows machine. I run the same thing on my Linux machine. I get 775. Of the ones I know, 272 are garbage collection related. You end up tuning this a lot when you start working on big systems with big amounts of memory. And I find there's loads of people fight the garbage collectors in production just to get them to work a lot. Now, we've been told G1GC is going to make our life so much better. I've been trying it on lots of different production systems, and compared to CMS and the likes of incremental CMS, I think it's dead on arrival. It's taken far too long. It's arrived here, and it makes things worse, not better. And I know a lot of people who are working in this space are finding very, very similar things. So what are our options? We don't have a decent garbage collector in the JDK. If I want to work on very high performance things with very large amounts of memory, what's my options? Well, generally, I ended up earning a good living by doing a lot of stuff off heap and doing effectively C programming inside Java to make it work. And if you're in the financial space, this is incredibly common. We don't end up allocating objects. We do lots of stuff off heap and doing lots of stuff with unsafe. The other option is you buy something like Azul's C4 collector, which is concurrently compacting and will give you pause times down to the millisecond, so it actually hides a lot of that. But the general JDK does not help us. It doesn't make the world much better. This one's probably going to start to end up annoying some people. I hear this a lot. Functional programming is going to solve all our concurrency worries. It's kind of interesting. Functional programming is great, but I hear this a lot. This is one of the things I hear quite often shortly afterwards by the uninformed, is the runtime will optimize all our immutable values. My favorite question to that is, how? I've spent a lot of time studying JVMs and other VMs, and I have personal friends who have worked on many of them. And we don't know how this actually happens, yet people go around claiming it quite often. In fact, it's much worse than you think. Final variables or final fields in Java don't actually become final. There is no constant propagation on them. And why is that? Because certain open source projects had gone and modified them with reflections. The JVMs can't even make them final. We're not able to do that because a lot of this is quite broken. So we've got to be really careful, people running around making statements about how this is all great and how it's all going to get better. Eric Meyer has got a great description of this, and he's a great functional guy, and he believes, a lot of these people believe in magic ponies. And this is how their world is good because of the magic ponies that sort everything out and make everything great for them. But it's not actually true. You have to understand how things work and work with what you have. So let's have a look at some functional programming techniques that are actually really great for being able to reason about your code. In principle, we basically have to deal with immutable values. Because if I have a reference to something, I need to be able to trust that it will not change, and I can apply a function to it and get another structure afterwards. That lets me reason about my code in a really good way. It's very, very useful, but it has implications. So how do you do that? Well, effectively, everything are trees for any sort of interesting data structure in a functional language. And if you make a change, what you have to do is path copy. So in this example up here, I have organized a group of letters, and I want to introduce the letter E to the structure. What I have to do is I want to reuse as much of this as I can, so I have to path copy from the leaf right up to the root and swap the root to point to the new structures and take back as much of the existing structure as possible. This lets me work on this reasonably efficiently for going forward like that. And it's a very nice way to hold on to reference to something that is truly immutable and not going to change. Now, what's a decent implementation of this? Clojure has one with their try implementation. This works really, really nicely. It is not concurrent. So people say functional programming is going to solve our concurrency issue. Well, what you have to do is you have to cas in the structure for the root, and we'll talk a little bit about this in a second. There are concurrent versions of some of these structures, but they're not persistent structures from the ones I have seen. They end up behaving very differently and more like a typical structure you'll have in another language. So let's look at a real-world problem. This is kind of interesting, what most people don't talk about with this. So I'm going to deal with the financial world. And I want to have a map of markets that I'm working in. This is a very common thing. Those markets will have certain venues in which we trade. In those venues, we'll have instruments that we're trading. So that might be gold, it might be sort of different stocks and shares, it might be financial instruments. Then there'll be orders placed upon those instruments. Like models end up with some level of complexity and some level of depth. Now, getting back to what I said before about path copy, if I make a change at the bottom, I have to copy the whole way to the top of the tree. So, if I want to add a new order, it needs to be added into the map here, which is part of the instrument, which is part of another map, which is part of the venue, and it works its whole way up to the top. And then at the top, I have to, what is known as cas, I do a compare and swap. It's an atomic level instruction a CPU can do where you can just swap something. So you can read something and you can swap something in if it has not changed. If it has changed on you, it won't swap it in and it lets you know that's going to happen. It's a fundamental concurrency primitive. So what happens is I have to take my tree, I add the new node, I build the tree right up, copying everything to the top, creating a new structure, and then I cas it in, ready to go. And if that world is great, it's fine. Now, in the concurrent world, we want multiple threads to do this. So what will happen is sometimes two threads will race. One will start copying, the other one starts copying. They build their way to the top, and one goes for it, and it gets there first. The second one goes for it, and it fails because it's been beaten by the other thread. What does it do at that point? Well, it has to just start all over again and go around a loop. It builds its tree up again, copying it all, and cases it back in again, and it might succeed the next time, or it might clash with another thread that's doing this. You get cas failures as a common problem here at the top. What's interesting is there's 3 dimensions to this problem. As your model gets deeper, your odds of this happening increases. As the number of threads you have increases, the odds of that cas failure increases. And also with the transactions per second increasing, that also increases. And hang on a minute, we were talking about concurrency as the way that we want to be able to scale up, use all of these cores, and if functional is going to solve this problem, these things are going against it because the more we throw at them, the more likely this is to fail. Now, it still has the great semantics of being able to reason about the problem. That is good, and that's something we want to preserve. But the claim that it solves the concurrency problem isn't stacking up in this case because the fundamentals just don't work. Now, what's happened whenever you actually measure this, and I've done this, I've built a couple of systems side by side in different cases. Different financial systems were built an imperative-based design for a financial exchange. I've built market surveillance systems that are doing the same sorts of things, and they're using these structures. I actually like using these structures for market surveillance because I can hold a reference to something and I can walk around the tree and it doesn't change on me, and then I can step forward to the next step in the market changing. Really, really useful. But what did I find out? These techniques are more than 10 times slower for throughput than basic imperative techniques in a concurrent environment. It does not solve the concurrency problem. What's really even more horrible is they push the garbage collectors completely into their sore spot of operation, not their sweet spot. The sweet spot is everything dies young. You use it and you throw it away straight away. These things start to hang around for a reasonable amount of time, but also they're not immortal, so they're right in the worst case scenario for a generational garbage collector. And I've seen garbage collectors go into meltdown trying to cope with some of these structures. Moving on to number 4, I often hear domain models don't perform. You can kind of translate this into object models don't perform. That's really what people are saying. Oh, the distillation of indirection is bad. It is kind of, in a micro level, that's true to an extent. But what I've quite often found is, if you want to build something completely specialized for a purpose, that's fine. It will follow a certain set of patterns. Like, this is an X-15 plane. It was the fastest plane ever built, 4,500 miles per hour, incredibly quick. Can't take off from a runway. It needs to be launched from under a plane. It's very, very specialized for exactly what it's doing. Most of us end up working on things that are much more general purpose and much more useful. And what that typically means is you've got multiple ways into a model, not just one way into a model. And when you've got multiple ways into a model, you can't build it highly specialized in the same way to perform. And so there's a lot to be learned from good modeling techniques and actually applying them correctly. Now, some of what I've learned, and I've learned this through measurement and experience, is good cohesion in code. It's really important to have good cohesion and low coupling. And if you do have good cohesion, you get a lot less cache misses. I've got a really good example of this where I was working on a high-performance messaging system, and people were getting obsessed with trying to tune different parts of the code. And I got to a point where I was getting uncomfortable trying to reason about the code because it was so complicated and so tangled. And knowing enough about how CPUs work, I was figuring that actually some of their techniques and where they're going with this are not good and are actually probably going to slow down code. So we took a few days and work through trying to keep the code as cohesive as possible, trying to untangle it as much as possible, but not work on performance, just get it to the point where we could reason about it better. After a few days of doing this, we had the code much cleaner, much easier to understand, and then we benchmarked it. After benchmarking it again, we found it was 30% faster. And people had been fighting to get 1 to 2 percentage points by twisting it out of shape for months before that. And just by cleaning up the code, we got a 30%. And whenever we measured it and looked at why, it was because of cache friendliness around cohesion. And the main thing that was biting the existing code was feature envy. You had classes that wanted fields that were over in another class, and you were calling getters all of the time to get things that really should have been across in this class, and it made it much, much cleaner. When you moved them across to this class, they were together in the same cache line. They were taking use of that bet that the cache system makes on things that are spatially together will be used together. Work with the hardware and get the benefits out of it. So that was a kind of big lesson in that just going for good, clean code really, really helps. We also found that just keeping it clean and keeping it small, the optimizers done a much better job, the CPUs predicted it so much better. And so writing really fast code quite often is not weird. It doesn't look horrible. It very seldom is that way. Good, clean, small code often is some of the fastest code you'll actually see, especially in general purpose applications. And in general purpose, I'm even talking about financial applications and other things that are quite extreme on the performance front. So you can achieve great things with this. What I have found sometimes, but is you need to specialize access paths. And so whenever I go into a model, I'll work in an area, but sometimes I've got to jump into a model. I've got to find a particular customer. I've got to find a particular order. The place where you start doing some of the weirder things is usually in indices. And those are where you get some really interesting data structures, like how do I find something, and things like sort of bitmap indices and all sorts of interesting things can get you to stuff really, really fast. So I'd say spend time on choosing your data structures really well. So the right data structures in your code for the access paths you're going to follow, and the right data structure for jumping into that model at the right place, and you get great performance from it. Number 3, we keep hearing this, we have to go parallel to scale. We've got to use all of these cores. This is what makes our code faster. I probably hear this almost more than anything. It has become the golden hammer. People are bashing screws in with this. They're not nails. Now, the one thing I've learned about everything I've ever done in technology, every choice you make has consequences. Knowing the consequences of any given choice. So, I have a problem to solve, and I decide to go parallel. I now have 2 problems to solve. My world just got a whole lot worse, and it has consequences. So once we start going parallel, we start having lots of fun. We start playing with lock-based code. It's actually slow. It's horrendously slow when you start using locks. They also deadlock. I teach a concurrent programming course using lock-free techniques. But for part of the course, I get people to do algorithms with locks and without locks. And every time I see people in the lock-based part of the course, they get stuck in deadlocks, they get tied up. Many people don't even finish the exercises, yet we believe this is the way we should be working. Threads and locks, yay. No, really not good. Well, we can use work pools, but generally they're really inefficient in how they're implemented. They can be done much, much better. Who's ever worked on a large project that used MapReduce or fork join? One? What was your experience like debugging it? Anybody feel like jumping out the window partway through that? Or trying to hire developers that have even the slightest clue how to do this reasonably well? It's okay reading a little blog post and implementing a simple problem. Try to build a big system with one of these. It can be fun. And then you'll see things like parallel collections. I see this really, really often. So many times parallel collections are so much slower than the single-threaded alternatives. I've seen this happen over and over again. It's amazing how well some single-threaded code can run. So, I find this to be so true, is that single-threaded rocks. There is a large financial institution, who I won't name, who went on a 3-year project to build a software transactional memory framework on which they would build all of their future systems. 2 years into this 3-year project, they weren't really doing very well. They could only do a few thousand transactions a second in little test cases. It was very buggy. It was always falling apart. And they hadn't even begun to think about high availability. And they were really worried about how they were going to do that. I got called in to help them. And having looked at it and having looked at some of the business problems they were looking at, I says, guys, try something different here. How about just write the business logic in a single thread and measure it and see is it fast enough for what you actually need. Now, their STM system was doing a couple of thousand transactions a second on trivial little problems. They wrote it single-threaded, nothing fancy, and got it working all within a few months. Now, I think they're 2.5 years nearly down the line with this other project. They could do 70,000 transactions a second on a single thread afterwards, and it did everything the business needed. Why did they go off building this STM system in the first place? It's like, do this, but be very careful. Now, if you do build good single-threaded code, you can actually scale by having message passing happen between chunks of data. So you keep things well decoupled, working on its own data. It actually scales really nicely. If that isn't scaling well enough, you can quite often just pipeline a problem. And actually, if you look inside CPUs, you look inside how humans organize things in factories or anything, pipelines work incredibly well. But if you really have to, you can hit the big nuclear button and go parallel. But it really helps if you've got people who know how to do it and know how to do it really well. The best people I know at doing parallel programming, their first choice is not to do it, because they know the consequences of it and how to do it. We need a lot of help to be able to reason about this and do it better. Moving along, logging's cheap. Code is usually littered with logging. It's hilarious. This is actually number 2 because it's the number 2 bottleneck I keep finding in code. And I've been checking with lots of colleagues who do similar things that I do, going helping people get code to go fast. And this is always the sort of second thing that sort of bites people. Why is it always at the top of the list of things we see? Well, let's say we're just going to pick on Java for a second. Other languages have got their own problems as well, but I'm just going to pick on Java because I'll condense it down a little bit. The 3 major sort of culprits in this space are log4j, logback as the replacement, and the Java util logging that's in there. They actually all work very similar in a general regard inside. They have got different tweaks to them. They will argue a few percentage points faster than each other, but actually they're worlds off what's actually possible. So I tend to generally ask a couple of very simple questions, like, should a logger be able to generate more data than you can actually write to a disk? You'd like to think so, but most of these things can't. They're so inefficient. The disk is not the thing that actually slows them up. What's even more staggering is quite often, if I add more threads to the problem, I should expect to be able to generate more data because they should be just generating data independently. Logging is a completely parallel problem. There is no contented data, yet these systems do not scale up with threads. Let's actually prove that with a real experiment. This is Java util logging. Other loggers are very, very similar, so it's not just the fault of Java util logging. This is the time taken to log a 50-byte message, only 50 bytes. And I want to start with one thread going as fast as I can, and then I'm going to add threads to it. It will take me 16 microseconds to log a 50-byte message into that. I go and I add a second thread. My average time goes up to 32 and a bit. And look at this, it's almost a perfect line. What you're seeing inside here is Little's law in action, forming a perfect queue for the logging system. It does not allow things to happen in parallel. And this is the average. It doesn't show you some of the worst case scenarios, because some of the worst case scenarios is what happens whenever the internal buffer fills and it goes to write that down to disk. It actually still blocks the threads that are writing. I see people starting to add appenders to try and fix some of the issues in here, but they're basically putting sticky tape on a problem that needs a fundamentally different approach to it. So I'll say, should logging be synchronous? It's fire and forget. Yet all of the design is synchronous. It uses locks and it ties everything up the whole way through it. I'd also question, why are we logging strings? It's okay in development because we're just looking at it and debugging it, but in production, it's huge amounts of data. It has to be processed, and then how do you analyze a significant amount of data that's string-based? You have to parse it, and it's soft and fluffy and generally wrong. This should be structured data that has some semantic meaning if we're going to process it later on in an automatic fashion, and strings are not the way to do that. Also in our code, I've profiled systems, and this is no joke, where if I actually looked at some of the time taken in the system, I found like sort of near the top, so 6% of total CPU time spent in is debug enabled. Not the code inside, just is debug enabled. You've got all of this going on. You've increased the complexity of the code by putting guard conditions around it, which makes it harder to read and makes more instructions to be processed by the CPU and increases the complexity of the methods, which makes them harder to inline and work with. Logging should be so fast and so simple, it should not need a guard condition. But we have them because it's so slow. Also, a really interesting thing around logging reliability. The way most of them work is they write to an internal buffer. And when that buffer fills, they write it down to disk. And that's how it works. And like say, for example, most of these usually are wrapping a buffered output writer. In Java, for example, internally by default, that has an 8 kilobyte buffer. It happens to be 8 kilobytes because that's the page size of Solaris, even though we're all running on Linux mostly these days. We will stick with the Solaris defaults for how that actually works. Now, as I start writing to that log over and over again, guess what happens just before I crash? If I was to crash, I'd probably have written some of the most interesting details that would help me tell why my program actually crashed. But it's lost because it's in that buffer. We should be logging to buffers that are out of process so that if our process dies, we actually know why, or we have a chance of knowing why and what is there. So I think there's some real fundamental design decisions in logging and the performance around logging, and we could move forward a lot if we address this. Now, my favorite one at the end is, people keep saying it's only parsing code. Has anybody profiled an application end to end and see where the time is spent? Did we do that? How much time have you found in business logic compared to parsing code? Mm-hmm. Yeah, I see in even reasonably well-written applications, the business logic is a rounding error. It's quite often not even 1%. We spend all of our time converting things from one thing to another and reparsing over and over again. We'll be converting JSON, XML, SOAP, all of this stuff. We're in this matrix of tag soup. That's what our CPUs spend all of the time doing. A good friend of mine runs data centers. One of the things he loves to do is take developers out to the data center, shows them all the racks and racks and servers, and you sort of explain where the time and the code spent, and you just bring people up behind them, and there's so much heat. There's all this heat getting blown out of the back of it, and he said, just feel that. That's your inefficient code. That's what we're mostly doing. We're parsing tags and turning these tags into heat. It seems to be what our main job is. Every now and again, we generate a stack trace. We seem to, as a very small thing, as a side effect, do some business logic occasionally. And so we spend so much time doing this over and over again. And ask some sort of basic questions. How much text do we parse that is not ASCII or UTF-8? Yet we convert everything to things like UCS2 and copy them between buffers and sort of expand them out from a byte to 2 bytes or whatever other encoding format as we're going through this over and over again. We're turning numbers in really inefficient ways from one form to another. It's really quite scary, and where all the time's spent. We're constantly parsing primitives and different things like longs, doubles, dates, times, and it is scary how much time we spend in some of this stuff. All of the libraries that we have as standard libraries can be so much faster. Some of them can be 10 times and even 40 times faster than what we currently have in some of our libraries that's currently out there. We don't get them fixed. We don't get them improved because people are not calling for that to be improved. We're calling for syntactic sugar. We want things like lambdas and we want all this sort of cool stuff. But we're not getting anything that actually makes much of our code faster. Like some of the things like lambdas and stuff that are coming in, going to make it even harder to optimize because we're going to be hit with polymorphic dispatch for a lot of these problems unless we can work out sane ways of dispatching these calls quite quickly. So we have to watch out for what's going on here. Now, what sort of things are horrible? I'll sort of pick up on a few things. I was dealing with an application last year that all of a sudden, when moving forward in the JDK, got massively slow. It exhibited parallel slowdown. That's a concept whereby whenever I add threads to my system, I should be expecting it to go faster, but it actually got slower. There was no locks in this code. We thought there was nothing shared across the code. It was actually designed to not have contention points. After a lot of profiling, we dug in, we found out what the problem was. HashMap had changed. Inside HashMap, there was a change to randomly seed how we sort of hash into the thing. So our hash key, we needed a seed into that hash key. It used Java random to do that, which is actually contended. And people go, well, that's not an issue. If you're parsing XML and JSON, you're building hierarchical structures using maps usually all the time, and it just chokes the whole application and it doesn't perform. Another thing we see very, very often is things like date and time parsing. Simple date formatter is not thread safe. So we have to create a new one every time we're parsing. That's really costly. Well, we can make it a bit better. We can stick it in thread local. You don't have to go through creation, but thread local is not as cheap to get at as we'd like to. It should be as cheap as C, but it's not because we have got some API design issues inside the JDK, and that could be much better. So we could be using Joda time, for example, instead, which is thread safe, but it's not faster. In fact, it's a touch slower than actually what's there. You can build versions of date time parsers that are 40 to 50 times faster than what we have in the JDK. You get so many requests. You get an order in for most things, it's got a date and a timestamp in it that has to be parsed, and we waste a shed load of cycles on that. We also spend loads of cycles in some of our API designs. We should be having designs with callbacks and iterers and things that don't cause us to copy memory all the time. For example, split on a string returns you an array. Why not return an iterable and iterate through the things that are in there? You wouldn't have to allocate the huge array. We get the design of some of these things wrong. We've got to think about the cost and the consequences of what we have and what we're doing. So one of the questions I find people keep asking is, once they start having systems and they want them to perform and they want them to go well, they say, where do I start? It seems like a mountain I've got to climb. How do I get my code so it's running better, running faster, and start learning all of this stuff? And I think it starts with one very simple thing. Get some performance tests into your code. Because once you've got some performance tests, you know where your time's been spent. You know what things are doing, and you don't get so surprised. You can then start profiling, you can start doing lots of other interesting things from that point. But without instrumentation and measurement and applying science, we're in the dark, we're guessing, and we're using folklore. And at that point, I'm out of time, and there's only 2 minutes left. So I'll take some questions if we've got any. Yes? Thank you. Yes, what's the question?
Okay. So at one point you said that J1 is slower than, so I have two questions. At one point J1 is slower than CMS. It's not my initial experience. Can you provide us with some scenarios in which this is the case? And the second one, you said that the logging was the second bottleneck, the second most often bottleneck you found. What was the first?
Okay, so in the two questions, first one on the issues with G1 and the fact that it shows up as being worse than CMS, particularly for low latency applications. If you try to tune G1 down to give you a repeatable low latency time, I found on many financial applications, and a number of other people have confirmed this, that we cannot get G1 to be within half of the time, or it takes at least double the time to do a minor collection than CMS does, or any of the existing parallel new collectors that are in there. As heaps get bigger, what it tends to do is it looks okay for a while and then has a bit of a disastrous case because one of the problems it has is it sort of clears out different regions of the heap that are supposed to be not very occupied. In theory, that's okay, but what we tend to find clustering in our applications, and say, for example, a cache, you get a small object with the caches pointing to the things within it. The problem we have to move is when we move that object to somewhere else in the heap, moving of the object's easy. The hard part is moving all the references that point to it. And you end up with objects like caches spidering through your whole heap, and copying all of those references can take a long, long period of time in the experience of some of the applications. I think it hasn't been out there long enough to really get enough profiling data, and there may be very good cases for it, but the people I know in the performance space aren't currently seeing that. There's a good argument for the amount of effort that's gone into G1. If that was added to incremental CMS, we would be in a much better position now than where we happen to be. The second question was, what is the number one thing I see in code? Was actually the number one point. Parsing code is quite often the biggest time-sucking applications, especially if you're doing WSDL or anything parsing XML coming in at the front end. We've got no more. Thank you.